Great. So, hello everyone. Welcome to our first session of the morning here in the main room. Our first speaker is going to be Okke. He is the leader of the payment machine learning team at Uber, which, among other things, works on automatically detecting fraud in payments for Uber services using machine learning. And he's going to talk to us about his team moved from correlation-driven machine learning to causal-driven machine learning and how this helped to improve key business metrics. So please give a big round of welcome to Okke.
Good morning, everyone, and thanks for the warm welcome. My name is Okke. I work on machine learning at Uber, and today my talk is about personalization, and specifically how causal-driven machine learning plays a critical role into how we do personalization at Uber. So a quick introduction on the agenda for today. First, I do want to talk a little about Uber in Amsterdam. One of the things I've noticed so far throughout the conference is that not that many people actually know we have a tech presence here in Amsterdam, so I do briefly want to touch about that as well. And then we are going to talk about the topic of CausalML. I'll give a brief high-level introduction, and then we're going to talk about the fun part, a case study of how we applied it at Uber. But first about Uber in Amsterdam. So we recently opened a beautiful European campus here in Amsterdam, close to Amsterdam South at Tripolis Park. And there's roughly 1,000 people working from there, which are split between our EMEA operations and the tech hub. So most people know that EMEA operations happen from Amsterdam. Not many people actually know we have a beautiful tech hub here as well. There's roughly 300 people spread across engineering, product design, and data science working on all kinds of problems, but most specifically, we work on global payments from Amsterdam. So that's the team that I work for as well. A small plug, we are hiring as well, so if you're interested, check out the link. So I lead the ML team here in Amsterdam, and some of the use cases we work on have to do with payments. The first one has to do with incentives. That's also the case study, so I won't go too deep into that as well. But we, for example, also work on payments fraud, where we try to make sure that we detect fraudulent users on the platform and prevent chargebacks from happening. Then we also work on things like financial products, where in some of the markets we, for example, offer loans to the drivers that work for us, and we leverage machine learning to make sure that we give the loan to the right user. So that's on a brief overview of what our team does. And a key part of the technique that we leverage for some of these problems is CausalML. And it's pretty interesting for me so far already see the topic of CausalML being brought up in multiple talks so far, which is super encouraging because also for us we've seen the value it has. And if you think about what makes CausalML different from classic ML, is that classic ML focuses on what we call association, if you follow the framework from Judea Pill, where you have specific features in the context of supervised learning, and you have a response variable, and you try to ensure that the features correlate with a specific response variable. CausalML, however, focuses on the intervention. What happens if we take a certain action? And from a business perspective, that's ultimately what we're interested in because we're in the business of making sure that we make the right business decisions. So in that sense, also purely on a theoretical basis, CausalML makes a lot more sense than classic ML. And when you look at the data, you also see that they have different data structures. We all know how typical classic ML data sets look like with, again, typically an X, which is your features, and then you have your Y, which is your target label, which is what you're trying to predict. Most supervised learning problems look like this. A classic ML problem looks very different from a causal ML data set in that sense, where you also have your features and your Y response as well, but then we introduce what we call the W column. So this has to do with the intervention. And the interesting thing about causal ML is that we need to predict the counterfactual value. So what you see here with Y0 and Y1, for every user or every unit in our training set, we can only observe the outcome for one of the actions. So if we, for example, give one business decision to you and another business decision to the other person, we can only observe once. So the key question behind CausalML is how can we estimate that counterfactual value? So that data set, that sense, looks also a lot more different. A key part behind effective CausalML is what we call randomized experimentation, often referred to as running a B test. And there's a few key assumptions that need to be met in general for effective CausalML. But the biggest benefit of running A/B experiments is that you satisfy these assumptions for free. And one of the nice things about working as Uber is that we run a lot of experiments. At any given point in time, there's over 1,000 experiments running, and all of these experiments kind of give us training data for free. So we run, for example, experiments across riders, trying out different versions of the home screen. Maybe we want to test out a new experience for the drivers. We run an A/B test for that as well. Or maybe even new versions of the ranking algorithm, where we train a new model that we want to compare with the old version. So experimentation in that sense for a CausalML perspective gives us a lot of free training data, which is great. And ultimately why CausalML is such a key part to our personalization strategy has to do with the individual treatment effect. If we think about A/B testing in general, what we're interested in is what we call the average treatment effect. You have to make a decision based on what works best on average for the entire population. In that sense, that's where that average treatment effect comes from. But there is some suboptimal decision-making here because you have to make a choice where some others might have preferred the other choice. So that's where ITE, or individual treatment effect, comes in, because with CausalML, you're able to estimate for every user what is the most efficient decision. So rather than giving a sort of a one-size-fits-all decision to everyone, we can focus on the individual, and in that sense, it becomes a key part of how we approach personalization. So that's how it works on the high level. But now to the fun part of the case study at Uber. First, I want to see a show of hands. Who here has ever received a promotion from Uber, either by email or SMS? A lot of hands who has received more than one. For a consumer-focused business like ours, promotions and incentives are a key way for us to attract users to the platform, either by attracting new users or to make sure that existing users spend more on our platform. And optimizing how we spend that incentive has been a key problem for us to solve because there's a lot of money involved. So every percentage improvement that we make here brings more value to the business. And the goal for us is to make sure that the right promotion goes to the right user at the lowest cost. So assume here we have a problem where we have 3 different incentive structures. On the one hand, we have 10 times 50% off on your next 10 trips, or maybe 10 times 20% off, or maybe 10 times 10% off. What we ultimately want to do is to figure out for each user what is the lowest cost you would be converting to taking those next 10 trips. So if you are a user who would already take the 10 trips at 10%, we want to give you the 10%, because if we then give you 50%, we're basically spending too much money on the incentive for you to take an action that you would have otherwise taken as well. So that's ultimately what we try to predict is what is the highest incrementality, that's what we typically refer to make sure that our campaigns and our incentives are as efficiently spent as possible. So our typical workflow on a high level looks like this. So usually we start with an experiment where we randomly assign different treatments to a broad set of users. And the goal here, as I alluded to earlier, is that with experimentation, you satisfy the assumptions behind effective CausalML for free. So running these experiments allows us to create that training set without really having to worry about that problem of the counterfactual. Then the second phase, we combine the data that we've gathered from those experiments with features about individual riders. So this, for example, has to do with how did this user interact with the previous promo, how long have they been active on the platform, features that relate to how are you acting on the platform so far. So by combining those features with the experiment data that we gather from those randomized experiments, we create our data set. And then we train our model and basically use that to select riders. So by being able to estimate the individual treatment effect for each of the riders, we can figure out we should give this specific promotion to you and that promotion to another one. And that way we can make sure that the campaign is spent most efficiently. Then for some of the campaigns that we run, they are one-off. So we run an experiment, we execute the campaign for the broader population, and that's done. For other campaigns, however, they may run continuously. And for that, especially if you think about from a retraining perspective, we need to make sure that we continue to gather that randomized data so that we can, for example, in a couple of months, retrain that same model again with a clean, randomized data set. So there's sort of a suboptimal execution of that campaign here, but that's a fair trade-off with long-term retraining of the models. So that's how it works on a high level. But now to the fun part of how it works under the hood. So if we come back to our problem statement, ultimately we're trying to make sure that we make the optimal decision of who should get the promo to maximize what we call incremental GB. So GB is what we refer to internally as revenue, subject to a specific promo budget constraint, because a lot of these campaigns have specific campaign budgets associated as well. So there's a few components to it here as well if you look at the formula. The first one has to do with incremental GB, again, revenue. We have both the revenue for the users who do get the promo and the users who don't have the promo. But the goal for us is to estimate what would have happened if you were in the other group. Another part of this is that treatment decision. What is the variable, the W variable here? So for example, 1 for treatment or 0 for control. And then you have the cost that we are spending on the promotion. So sometimes these campaigns, as you saw in the example as well, are percentage-based. So these are not hard dollars, but they are percentage-based of 10% off in the next 10 trips. So we also need to estimate how many trips are you actually going to take, what is the value of those trips. So for us to be able to estimate what the cost is, we need to not only know how the promotion looks like, but we also need to know how much money are you actually spending, because the cost for us on that incentive is 10% of the revenue that you're spending on our platform. And that, again, that cost is subject to a specific budget. So that is overall the problem statement. So if you break it down to our ITE estimation framework, there's essentially 2 key components. One is our spend estimator, where again, we need to estimate how much money are we spending on that specific promotion for that specific user, and we want to be able to know that for different incentive structures. Then we have what we call the GB estimator, where we basically try to predict how much money are you spending on the platform and how much money are you spending on the different circumstances. So we need to be able to see if you are assigned a different promotion, how much money would you then be spending on our platform. That together forms into this efficiency metric, which we call IGB per dollar spent. So essentially, what is the ROI of a specific campaign? And for a lot of the campaigns that we run, we also have minimum target values where we need to make sure that our campaigns are run as efficiently as possible. And that IGB per dollar spent is also a combination of the spend estimator and the GB estimator. So you can already see the formation of the interdependency between the different tasks that we need to estimate here. So if you sum that up in the overall task that we are working on here, is that we need to learn estimators for 3 different things. So one is the estimator for spend. How much money are we spending on each individual promotion? The GBs for all of the treatment groups involved. So if you are getting one treatment versus the other, we need to be able to estimate how much money would you otherwise receive. And then, of course, we need to estimate that IGBS, our efficiency metric, which is both a function of GB as well as spend. So if you think about it, there's a few challenges with this. The first one has to do with just what we call the fundamental problem of causal inference, and that is only one of the observations we can observe. So if you are assigned to one specific treatment group, we only know what happens in that specific treatment group, and we don't know necessarily what happens in the other treatment group. Now, the fact that we use randomized experimentation to generate our training set helps us solve that fundamental problem. The bigger challenge is, however, is how to do this in an efficient and scalable manner. Because as you see on the estimators here as well, there's a lot of interdependencies going on here where how much we're spending on the promotion depends on how much money you're spending on our platform. So there's all these interdependencies happening here where on the surface they all look like individual estimators, but behind the scenes they all depend on each other. And how to do this at an Uber scale makes the challenge even more complex because we have on average 100 million users active on the platform. So for us to be able to figure out this user should have this promotion and this user should have that promotion is an extreme challenge for us sometimes. So if you break it down, these are essentially the 4 estimators that we want to estimate. So we have our spend estimator, our treatment GB estimator, our control GB estimator, and then our IGBS estimator. So for problems that in the past we sort of treated like independent problems. So we would, for example, use traditional machine learning where we would individually estimate all of these values. But as you saw in the previous slides as well, there's a lot of interdependencies happening here where all of the functions, all of the estimators kind of are dependent on each other. Again, the amount of GB that you spend on the platform is a function of which promotion you get. The amount of cost that we're spending on that specific campaign is also a function of how much money you're spending on the platform. And we saw that in the past, if we treated that as separate estimators using more traditional machine learning methods as part of the CausalML ecosystem, is that we were not necessarily able to capture that interdependency. So it did work for quite a while, pretty well in terms of how we optimized our incentive spend, but we did realize that we weren't able to capture that interdependency. And that's when we started thinking a little bit more about how do we want to solve that specific problem. And that's when we came up with neural networks. So one of the beautiful things about neural networks is they are much better at capturing that interdependency between some of these estimators, especially thanks to the unique properties such as backpropagation. It allows us to optimize multiple objectives at the same time and capture that interdependency between all of these estimators a lot better. And inspired by the work of, from work on Y-Learner, we introduced this architecture called multitask Y-Learner. And as you can see here beautifully in the visualization of how the neural network looks like, you can on the one hand see the interdependency between all of the individual parts of the neural network. So you can, for example, see that the promo features only impact the parts of the network that have to do with the treatment group. And that way we are able to separate the features, what we call the rider features, so that has to do with, again, what I alluded to earlier with how did you respond to previous campaigns and other behavioral characteristics that we can observe on the platform. And that together, in the past, we sort of treated as one data set, but by specifying it as a neural network, we're much better able to separate that from each other and still have one single neural network. So you can see here that we start with the rider features as part of the neural network, and then the promo features only impact the different treatment-related parts of the network. So that way, we not only have one single network that fits all of the estimators, where in the past we would have 4 different single models that would need to be run. So also purely from a scalability perspective, it gives us a lot more efficiency. So coming back to our initial user base. So usually when we start a campaign, there's an initial selection of users that we want to target. That, for example, has to do with specific geolocations. Maybe we want to run a campaign in the US or a campaign in the Netherlands, for example. And one of the things we've seen in recent years is that our business basically consists of 2 verticals right now. We have on the one hand our taxi business and on the other hand our delivery business. So in some markets that can be food delivery, and in other markets that can be grocery delivery. And one of the ways we've seen work most effectively for us is if we can upsell one user or one user using one vertical to the other vertical. And that way, especially with the increased spend on advertising dollars today, having an internal tool for us to basically serve as a marketing tool allows us to be much more efficient. So the overall usefulness of this tool for us to figure out, we have a user that has been taking trips to the airport for the last 5 years. Maybe they're now also interested in food delivery. Let's give them some extra discounts or some extra coupons for them to spend on the platform. It has become a bigger problem for us as well to do that more efficiently. So that's typically how these problems start out. And if you apply that ITE estimation framework, this is how that typically looks like. So on the one hand, we have our IGBS. So this is our efficiency metric where we're interested in what is the incremental GB that we're getting for every dollar spent. So for a lot of these campaigns, as I said earlier, we have a minimum efficiency target where we're interested in, where we sort of have a minimum benchmark that we want to meet for every campaign. Otherwise, we're not even interested in running it. And then we have the spend, which is again a function of how many trips you're taking on the platform as well. And then depending on the budget we have for a specific campaign, we can make that decision. So for example, here in the hypothetical example on the screen, you see that we have, for this specific campaign, a budget of 7. And our minimum target value for the efficiency, so the ROI of a given campaign here, is 2.5. So you can see here that we need to select only the first 3 users, because these are the only users that meet that minimum benchmark of 2.5. And that's the beautiful part of using hypothetical examples. They also sum up to a budget of 7 here. So that is how these problems are typically solved. And by ranking the users that way, we can estimate what is our overall effectiveness of the campaign. And what we have seen is that since we started moving from machine learning-based architectures to deep learning-based architectures, the overall efficiencies of the campaign that we run grew substantially. So capturing that interdependency of all these estimators separately allowed us to basically increase our efficiency target. And again, because upselling promotions to users has become more and more critical for our business, that was a key work stream for us, and yeah, that way we were able to create a lot of efficiencies here. A conference talk is, of course, nothing without a little plug here. So based on some of the learnings we've had from developing causal models at Uber for the last couple of years, a few years ago, we open sourced this package called CausalML, available on open source for Python. And based on the learnings we've had on developing some of these models at Uber, we open sourced this package with a few suite of uplift modeling algorithms. So this is both focused on the classical meta learners, as well as some of the neural network implementations as well. So I would highly recommend you to try it out if not already. And it's open source now, so we're always looking for contributors as well. So that wraps up my talk for today. With that, thank you so much, and yeah, open for any questions.